Okay, so the first question of the video problem is that we need to find the inverse Laplace transform of function h of s, and it depends on if the ROC is within a certain range or if it's causal or anti-causal. So to start, we can draw the graph of the different poles that we have. So the different poles are the roots basically of the equation, which is -3, -1, and 5. So to start, we can do partial fractions. So since the numerator order is smaller than the denominator order, we don't need to do a division to then find the partial fraction, so we can directly just go to the partial fractions. So by doing the Heaviside cover-up method, we can find that each of the coefficients are equal to 1 by chance. So after that, we can just write h of s with the coefficients written already in them. And now we need to find h of t by doing the inverse Laplace transform. So first of all, there is a Laplace transform property which says that x1 of t plus x2 of t is the Laplace transform of x1 of s plus x2 of s. So that means that the sum is going to stay the same, and we can just do the different Laplace transforms of each fraction. After that, we know that the inverse Laplace transform of 1 over s minus lambda is equal to e to the lambda t u of t. So we are going to use that to find h of t. And finally, we know that a of x1 of t is the Laplace transform of a of x1 of s. So we know that the coefficient just stays the same no matter what we're doing. So we can then start by graphing the different ROC sections. So let's say for A, the ROC is, it's when RE of S, so the real part of S is bigger than 5, so this part here. And then we know that it's causal and it's unilateral, so all of the roots will be positive. So it is going to be h of t is equal to h of e minus 3 of t u of t plus e of minus t u of t plus e to the 5t u of t. If we go to B, when R of E, RE of S is smaller than -3, meaning it's anti-causal, everything is going to be negative because it depends on the past, it doesn't depend on the past values of time. So h of t is going to be equal to minus e to the minus 3t u of minus t, minus e to the minus t u of minus t, and minus e to the 5t u of minus t. Now if we go to C, it is going to be a two-sided function between -3 and -1 here. So the function is going to be a sum of basically plus and minus forms of the fraction, because this side is going to be causal and that side is going to be anti-causal. So h of t is e to the minus 3t u of t, which is positive, and then we start with the minus side, minus e to the minus t u of minus t, minus e to the 5t u of minus t. And it's almost equivalent to the D, which is ROC in between -1 and 5. So we are going to find h of t equals e to the minus t u of t, e to the minus t u of t, minus e to the 5t u of minus t, since it is after the ROC.
The question 2 provides us with 6 polar diagrams and wants us to match each of the diagram to its impulse response. Simply, we can just directly get the poles and zeros from the diagram. So for the first diagram, we can just get s is equal to 0 and there's no zeros. So we can get h of s, the transform function is equal to 1 over s, and we can use just directly use the inverse Laplace transform. The inverse Laplace transform for 1 over s is just the unit step function u of t, which matches the third impulse function. And it's similar for the next 5 diagrams. For the second one, for the second one, s equals to -1/2 plus or minus j. So we can rewrite the transform function h of s. After the calculations, we get as 1 over s plus 1/2 squared plus 1, and use the inverse Laplace transform. You can directly get the impulse function equal to this term. And when we see when t equals 0, this thing just equal to this thing equal to 0, and it's a periodic. It's a periodic function, and because it has unit step function here, it has no numbers before 0, so it matches the impulse response for graph 1. And when we see the third one gives us s equal to -1, and there equals to 0, and we can also rewrite the transfer function like s over s plus 1, and we also use the inverse Laplace transform table to get the impulse function like delta t minus e to the minus t times unit step function. And when we try to confirm one, because there's a trick here, because it has a delta t here, so it will have an arrow, something like that. So it's only 4 or 6. But also when t equals to infinity, it goes to 0. So it matches the impulse response like diagram 4. And for the first one, s is just equal to -1. So the transfer function is 1 over s plus 1. And also using the inverse Laplace transform table, directly get e to the minus t over u of t, and it's easy to get. It matches the second impulse response. I will come to 5 at last because 5 is a little complicated, and I will explain 6 first. 6 is for 6 the s is equal to -1 plus or minus j, and that equals to 0. So h of s is equal to this term when we rewrite it into 1 over 1 s plus 1 squared plus 1. And I can also use the inverse Laplace transform table to directly find s equals to this term here, because there's also like a periodic function and with a unit step function, and so it matches the fifth diagram for the impulse response. And for the fifth, there's a different explanation here. I can rewrite the fifth transfer function like this term, finally get this kind of term, because by using the firstly divide the numerator to denominator, I can finally get this part here. And for this one, I can directly know the impulse response for 1 is just delta t. And for this part, I firstly use the cover out method to simplify the term here to get h of s, and also finally use the inverse Laplace transform table to get this number. And by further simplify this, I finally get this term, h of t equals delta t of the very last term, and it has the impulse delta of t here, so I can directly know there's an arrow here, and also it's a periodic function. And so finally, the fifth matches the last diagram, which is diagram 5, I think. Yeah.
6.
Oh, it's 6. Sorry, it's diagram 6.